And so another instance of sort of algorithmic bias you can see when using Google Images. Okay, so supposedly this has gotten better, and we can test that out ourselves, but in 2015, if you performed a Google Images search for nurse, what do you see? Yeah, you see almost all female presenting nurses in the image results, right? And so nursing is a female dominated sort of profession, but it's definitely not 100% female, right? And so this seems quite strange, right? And there's clear bias here, right? This is not reflecting the real world sort of a breakdown of genders in the nursing career. Now, let's go to Google Images search ourselves. Let's just search for nurse. What do we see now? So supposedly this has gotten better, but I think someone lied because it doesn't look much better. Right, it's debatable. You'll see for the next example we're going to do, it has gotten better, but still the search results are predominantly female. Not 100%, right? There's some male presenting people here, but you see we still have this issue, right? Even though there's nothing really at all inherently female about the term nurse or the profession nurse. Now in 2015 again, when you searched for doctor, what did you see? Yeah, mostly male presenting physicians. When again, there's nothing inherently masculine or feminine about any career. But let's see what happens when we search for doctor now. Okay. So this seems much better. Do we agree? Right, so something must have changed under the hood at Google Images between 2015 and now, because this seems like a much more representative sample of people who are doctors. Do we sort of see the difference? Okay. And so this brings up a broader question that there isn't necessarily a right answer to. Right? When I search for nurse or when I search for doctor, what am I really expecting to see in my results? Am I expecting to see the most common picture of a nurse or the most common picture of a doctor? Or am I expecting to see a sample of nurses and a sample of doctors, right? And that's not really clear. And it's also not clear whether or not the search results should be a representative sample of, a certain profession. Right? Because if there's a profession that, let's just say, is 90% female, well then seeing, similar images 90% of the time isn't really going to be that helpful when I'm searching, performing my search, right? Maybe I want to see different results in my images. Right? So this is something we need to think about, and it's like exiting the realm of formal data science, but it's something we still need to think about as data scientists. Okay, so if you're interested, there's this study that you can look into where sort of the conclusion was that people are pretty good at coming to a sort of judging what the gender disparity is in any given profession. But when you use, say, Google Images or whatever to look at pictures of people doing a profession, and you see bias in those image results, that bias that you see then influences what you think the gender disparity is in that profession. Right? So you have one belief, you do an image search, you see that things are way more skewed than you thought, and then now you think they're more skewed, even though they're not. It's just that Google Images is bad. You sort of see the issue here? Right, so this bias in the search results influences what you actually think about sort of the gender disparity in these professions. Okay? And so it's interesting to think about how this disparity might occur. What exactly is the Google search or Google Images search algorithm looking for when it's showing us pictures? And so one interesting way to think about this is that Google, it's based on PageRank, which is a system it uses to assign importances to web pages or importances to images. Right? You might have learned about this in Math 18, I believe, right? Maybe? Yeah, okay. And so what PageRank does is it tries to show you the most relevant images or the most relevant pages when you perform a search. Right? And so let's just say there's a profession that is, say, 60% female, 40% male. Right? Every time it tries to show you an image, it might just be trying to find the next most relevant image, but those all might be coming from the female category. Right? So even though the actual profession is, has a 60-40 breakdown, the images you see might be like 80-20 or something. Do you sort of see how that might happen? Okay. And so it's important to think about how this might happen so that we can start to think about, if we were building a system like this, how would we combat this, addition of bias into our system? Okay, and that's sort of what we're going to try and address with these parity measures. Okay, before we do that, I just want to add my iPad back as a second monitor. One sec here. Okay, there we go. Okay, so what I want to do now is make things a bit more precise. Like, mathematically, what do I mean when I say this algorithm is unfair or this classifier is unfair? And so to do that, we need a bit of notation. So we'll suppose that C refers to a binary classifier. And remember, a binary classifier either predicts 1, or the positive class, or 0, which is the negative class. So for instance, maybe C predicts whether or not an assignment was plagiarized, for instance. Okay? Y will be our variable for the truth, what you would predict if you had all of the right answers, essentially, right? So Y is our right answer. And A is some feature that we are interested in sort of studying further. Okay, you can think of A as being a group. So if A is 1, that might mean that you're a data science major, and if A is 0, that might mean you're not a data science major. Okay? So A, think of it as this group that you're either in or not in. Sound good? Okay. So when I say that a classifier is fair, what I really mean is that it performs the same for individuals in group A and outside of group A. Do we agree? Or does that sort of capture what we think of by fairness? Essentially, the performance of our classifier should be independent of group A. Do we agree? Right, if it's fair, that seems like a reasonable definition, but it's not clear what I mean by performs the same. Right, we just spent 2 lectures looking at different ways to quantify how our classifiers perform. And so each of those different ways of evaluating a classifier have different parity measures. And so let's look at some of those. So one way of quantifying if a classifier is fair is if it achieves what is known as demographic parity. Okay, and remember, A is the group, so you can think of this as data science major or not data science major. And C is what the classifier predicts. And so here we're saying a classifier achieves demographic parity if it predicts 1, the same frequency. It predicts 1 with the same frequency for both individuals in group A and individuals outside of group A. Right, notice demographic parity doesn't involve what the ground truth is. It doesn't involve Y at all. This is just saying we predict the positive class just as often for group A and outside of group A. All right? So essentially it's saying how often we predict class 1 is independent of A. And so this is a little abstract, but let's look at it in the context of a few examples. So pretend, again, that C is a binary classifier that predicts if an email is, or not an email, an essay is plagiarized or not. And let's just suppose A is the class is a science class. Okay, so if A is 1, we're looking at a science class. If A is 0, we're looking at a non-science class. Okay? So if our classifier C, which again is detecting if an essay was plagiarized, if it achieves demographic parity, then it should be the case that it predicts an essay is plagiarized just as often for science classes and not science classes. Do we agree? So if I look at just the science classes, it should predict 1 the same amount of times as if I just look at the non-science classes. Do we agree? Right, and so if our classifier satisfies this condition, we say it achieves demographic parity. Okay? There's another example we could think of. Right, and so this is related to one of our Google image search keys. C could be a classifier that predicts whether or not an image is of a doctor. Okay? And our attribute of interest here could be whether or not the image is of a woman. So if A is 1, the image is of a woman, and if A is 0, the image is not of a woman. Do we agree? Okay. So if our doctor image classifier, C, achieves demographic parity, then it should be the case that it predicts the pictures of a doctor as often as it does for women as for non-women. So it should be predicting this is a picture of a doctor just as frequently for women and non-women. Do we agree? Okay. So again, this is just like one way of thinking about whether or not a classifier is fair. But can you think of an example, perhaps in the context of either example 1 here or example 2 here, where demographic parity doesn't really make that much sense? Yeah. Let's not think so much in terms of like the dependent structure of random variables, but instead, just think about, let's just say, whether or not an essay is plagiarized. Is it necessarily the case that the classifier is unfair if it doesn't achieve demographic parity? Right? When might it be okay for demographic parity to not be satisfied? Yeah. Right. Right, that's actually a perfect example. Another one is, let me drink this before Another example is that, like, if we're looking at essays, it is probably, way easier to cheat on an essay in like a humanities class than it is to cheat on a science lab report. Do we agree? Right, because you could use Turnitin and whatever, right? And lots of classes use Turnitin. Right, so we shouldn't necessarily expect the classifier to predict that an essay was plagiarized just as often in science classes and not science classes, right? Because the rates of occurrence in science classes and not science classes are different. You see what I mean by that? Right, they're different, and so we shouldn't expect the classifier to work the same way, at least in terms of predicting positives in both classes. Do we agree? Okay. So what I'm getting at is that demographic parity is just one way of quantifying if a classifier is fair. It's not the only way. Right? Notice in demographic parity, the true label Y didn't appear at all. Here we were just making a statement on how frequently do we predict one. So how frequently do we predict that an essay was plagiarized? Another notion of fairness is accuracy parity. Okay, and this one might be a bit more intuitive. You see the word accuracy. We know that accuracy for a binary classifier, or really any classifier, is the proportion of predictions that it sort of gets correct. And so we say a binary classifier achieves accuracy parity if essentially its accuracy is the same for group A and for those outside of group A. Do we agree? All right, so that's what C equals Y means. Remember, C is our like Y predicted, and Y is our Y true. So this is saying the proportion of times our prediction is correct should be the same within group A and outside of group A. Okay, and so another way of thinking about this, if you want to think formally in terms of random variables, it's kind of like saying the accuracy should be independent of A, right? So you could say that like knowing what the subject is, whether it's a science class, a math class, an English class, whatever, that should tell you nothing about the accuracy of the classifier. Do we agree? Before we were, the like quantity that we were looking at the probability of was just how frequently the classifier predicts one. Right? So how frequently it predicts that, say, an essay was plagiarized. Now we are looking at how frequently it is correct. So it could be, a true positive or a true negative. Do we see how they're different? Okay. And so let's look at another example, and this is one that we will look at tangibly. Let's pretend our classifier is one that decides whether or not to approve someone for a loan. Right? So this could be for a student loan, for a car loan, a credit card, or whatever. Right? And let's suppose the relevant group attribute is whether or not the person is less than 25 years old. So if A is 1, the person is under 25. If A is 0, they are at least 25. Sound good? Okay. And so what does C is equal to Y mean in this case? Well, if C is equal to Y, then either we had a true positive or a true negative. What's a true positive? Well, a true positive is if we predict that someone will pay back their loan, and they actually pay back their loan. Do we agree? Because the only reason you would deny someone from a loan is if you think they're not going to pay you back. Because if you know they're going to pay you back, you would always accept it, right? Because they're just going to pay you extra interest. We sort of see that logic? Okay, so a true positive is you approve the loan and they pay you back. A true negative is you deny the loan and they don't pay you back. Right? And of course, this is a hypothetical because if you deny the loan, they would have no opportunity to pay you back because you never gave it to them, but think of it as like you deny the loan and they would have not paid you back. Or in other words, they would have defaulted. They would have said, I don't have the money to give to you. Right, so are we clear on what a true positive is here and a true negative is here? Okay, so if our classifier is correct, then either it correctly approves the loan or correctly denies the loan. And if our classifier achieved accuracy parity here, well then essentially it would correctly classify loans, at the same rate for young people and old people. Do we agree? Right, so it's, performing just as well in terms of accuracy for young people and old people. Do we agree? All right. So that's accuracy parity. Now, as you might be starting to infer, there are many definitions of fairness in a binary classifier. Right, we just looked at how frequently it predicts 1 and the accuracy. But remember, we also learned about recall and precision, and remember there's that big Wikipedia table of all of the different ways you can evaluate a classifier. All of those different ways you could evaluate a classifier also have their own parity metrics. So, which parity metric does this resemble? Here I've called it, which evaluation metric does this resemble? I've called it true positive parity, because that's what it's actually called. But here a classifier achieves true positive parity if the proportion of actually positive individuals, so people who actually would have paid back the loan, that are correctly classified, so that you approve their loan, is the same within both groups. Now, which evaluation metric does this kind of resemble? Right, the proportion of people that actually would have paid you back that you predicted would pay you back. Or the proportion of people that actually have COVID that you predicted would have COVID. What does that resemble? Close. It's not recall, right? Because remember, the recall of a classifier is the proportion of actually positive instances that you correctly identify. Right? The denominator was all of the actually positive instances. Right? And you can kind of see the resemblance here. The thing we are conditioning on is y is equal to 1. And this is the true y is equal to 1. So you can think of this as everyone who is actually positive. Right? And so here, essentially a classifier achieves true positive parity if its recall is the same both in group A and outside of group A. Do we agree? Right? And so that's true positive parity, but I could also use precision parity if I wanted to, right? Or false positive parity, or false negative parity, or whatever other parity I want. I just take one of those evaluation metrics that we learned about and then just see if it's the same within group A and outside of group A. Do we agree? Right, so this is essentially what you need to do in step 4 of your project 5. Right, you pick an evaluation metric, maybe precision, accuracy, the proportion of times it predicts 1, and you want to see if it's the same both in a group and outside of a group. Does that kind of make sense? Okay. And so let's look at how this might work a bit more tangibly. Okay? So I mentioned loan approval as an example, so let's go ahead and use that. Has anyone heard of Lending Club? Yeah. Yeah. So we're about to see how you would make a conclusion, and essentially it comes down to running a permutation test, and we're about to do that. Yeah. Okay. Has anyone heard of the Lending Club? Okay, a few people, but yeah, it's a peer-to-peer service that allows you to say I need a loan, and you'll get approved for a loan. It's like a digital service for that. Well, anyways, they used to publish a data set consisting of all of the loans that they've approved, and they stopped doing that. And so if you click the link that's in the slides, it's not going to work. But this was downloaded from way before, and so let's take a look at the data set. Okay, so these are all of the loans that they approved. Now, after they approve a loan, that's like them saying, hey, okay, here's $5,000. Please pay me back. Now, the number one thing they kept track of is whether or not they were actually paid back. All right, and so the tag column tells us whether or not they paid the loan back. So 1 means they paid the loan back, 0 means they didn't. So in all 5 of the instances here, did people pay the loans back or no? No, right, because all the tags are 0, but you'll see there are some 1s as well. Okay, what are the other categories or the other features? Well, there's the age of the borrower, the loan amount, so how much they asked for, employment length, so how long the borrower has been employed. Do they own a home, yes or no? Do they have any credit inquiries in the last 6 months? So this is one of the factors that credit card companies look at when you apply for a new credit card. Your revolving balance, does anyone know what this is? Yeah. Yeah, essentially. So it's like your credit card balance at the time that they made this inquiry. So essentially, like every month, American Express or whoever will like report how much your credit card balance is to like Experian or Equifax or TransUnion, and that is reported as your revolving balance. Okay, you don't even necessarily need to carry a balance for this to be reported, right? Because if I buy something for $100 today, even though my bill wasn't due, it'll still say I owed $100, right? So that's what this contains. And so essentially the goal is to build a classifier that predicts whether or not someone will pay their loan back given this other information. Right? And if I was able to do that, well, then I could pretend to be a bank. Well, I don't have enough money to be a bank, but if I did, someone could come to me and say, hey, can you give me a loan? I could put in their information into this classifier and then come to a prediction as to whether or not I think they will pay me back. And if I think they will pay me back, I'll give them the loan. If not, I won't give them the loan. Does that kind of make sense? All right. So let's try and build such a classifier. Also, just for fun, you can see that the total amount sort of loaned in this data set was over 5 billion. There's 3 zeros there, 3 more, and 3 more. Okay, cool. And there's just under 400,000 rows. Okay, so let's build a classifier that predicts whether or not someone will pay us back. So I've sort of arbitrarily decided to use a random forest here. I'm going to use all my other features, do a train test split, fit my random forest. What does n estimators mean in the context of a random forest? Yeah, how many trees that the random forest is made up of, right? Okay. It's taking a long time to fit because remember there are almost 400,000 data points. And so, 300,000 of them will be used for training because the default train test split is 25%. Okay, and so now I can use this classifier to make predictions. Remember, 0 means we predict they are not going to pay us back, and 1 means we predict that they are going to pay us back. Sound good? Okay. So what happens when I run .score? What's it going to show me? Accuracy, right? So for a classifier, the default scoring metric is accuracy. And it seems like we were 71-ish% accurate in predicting whether or not someone will pay us back. But as we know, we're not going to just look at accuracy. We want to look at these other measures like precision and recall. And to start doing that, we can plot a confusion matrix. And so, I guess one question to ask is, what was the most common outcome? A true positive, a false positive, a true negative, or a false negative? True positive, right? Because that's in the bottom right, and that number is 42-ish thousand. That's pretty big. Here's another question. Do you agree that the classifier makes around the same number of false positives and false negatives? Kind of, right? So I'm looking at the purple numbers on the off diagonals, right? So the top right and bottom left. Right? Which number is slightly higher? False positives or false negatives? I heard both answers. Someone commit to an answer. Which one's larger, false positives or false negatives? False negatives, right? Because the top right number, 12,000-ish, that's when you predict 1, but it was actually 0. So that's a false positive. That's slightly less than the 15,000, which we have when we predict 0, but it was actually 1. That's a false negative. Right? And so what does a false positive mean here? Well, it means we predicted that they were going to pay us back, but they didn't actually. Because remember here, the positive class is they will pay us back. So a false positive, which we had around 12,000 of, actually around 13,000 of, Those happen when we predicted they were going to pay us back, but they didn't actually. A false negative is when we predict that they're not going to pay us back, but they actually would have. Do we sort of see the difference between false positives and false negatives here? Okay, good. So, we may as well compute our precision and recall and interpret what they mean in the context of this data set. So remember, the denominator of precision is the total number of data points that we predicted the positive class for. Remember, you remember precision because both of the terms in the denominator have P, right? True positive plus false positive. Don't forget that. So here, the denominator is the total number of loans that we approved, right? That we predicted that they would pay us back. The numerator is the number of loans that we predicted they would pay us back, and they actually did. Right, so what this is saying is 77% of the time, if we predicted someone was going to pay us back, they actually did. Do we agree? Right? So 77% of the time, we said, okay, we think you're going to pay us back. Here's the money. 77% of the time, they actually paid us back. Do we agree? Right, and arguably, if you're a bank, this might be the most important criteria, right? Because you want to make sure you're not giving out money to people who are not going to pay you back. Do you agree? Right? And so it's worth thinking about what we would get if we subtracted the precision from 1. Right? So if we did 1 minus the precision, what would be the numerator? False positives. Right? So 1 minus the precision would give us the proportion of loans that we approved that wouldn't pay us back. Right? And so if we compute that here, what this is saying is, well, if 77% of the time they would have paid us back, 23% of the time, they weren't going to pay us back. So this is kind of bad, right? Because we approved a bunch of loans, and 23% of the loans that we approved, they weren't going to pay us back. So do we see why this is a bad thing if we were a bank? Okay. So that's precision in this case. Remember, recall has a different denominator. Looks very similar to precision, but the denominator has false negatives instead of false positives. So here, the denominator is the number of people who actually would have paid us back. It's not the number of people who we gave loans to. That was the denominator before. Here, the denominator is the number of people who actually would have paid us back. Their true tag value is 1. Right? And the numerator is the number of people who would have paid us back that we actually gave a loan to. So what is this saying? Well, this is saying, what? Can someone interpret this sort of in terms of English here? The 73% number, what does that mean? Yeah. Sure. Not quite. So what this is saying is there are some number of people who would pay us back. We only gave loans to 73% of them. Because the denominator is the number of people who would have paid us back. And ideally, this number is as high as possible too, because we want to give loans to everyone who would pay us back. Why? Because that's going to give us more money in interest, right? And so what this is saying is there are a ton of people who would have paid us back, but we only gave loans to 73% of them. Do we agree? Okay. And so if we take the complement of this once again, or instead if we put false negatives on the numerator, what this is giving us is the proportion of people that would have paid us back that we didn't give a loan to. So this is saying there's a bunch of people who would have paid us back, who would have given us interest money, but 26% of them we didn't give a loan to. We incorrectly rejected their loan request. Okay? First, do we agree with what this number is saying? 26% of the people who would have paid us back, we did not give a loan to. Do we agree with that interpretation? Okay, so this is bad both from the perspective of the bank and from the perspective of the person asking for a loan. Why is it bad from the perspective of the bank? Well, 26% of the people who would have paid us back, we never gave a loan to. which means we're not going to collect interest from those 26% of people. So we're losing money as the bank. Do you agree? Because if you're a bank, you want to give out as many good loans as possible, as many loans that people will pay back as possible. But from the perspective of the person who's asking for money or trying to apply for a loan, this is not good for them either, because they needed money for something and they were going to pay it back, but they weren't given the money. And maybe they needed the money to buy a car and they were going to pay it back, right? Because these are false negatives, but the loan wasn't approved. Right, so do we see why a high false negative rate, which you can think of 1 minus recall as, is bad for everyone essentially? Right? So again, the way you interpret this 26% is of all the people who would have paid us back, 26% of them were not given a loan. And that's not good. Do we agree with the interpretation? Okay. So, like I said, this 26% number, let's think of it as the false negative rate. So it's of all the people who are actually positive, how many did we predict negative? And that's essentially what this is, the false negative rate, 1 minus the recall. And so, remember, when we first introduced this loan approving example, our attribute A was whether or not the person was under 25. Right? So maybe we're interested in looking at the false negative rate for each age group. So the first bar is 20 to 25. The next bar is 25 to 30, then 30 to 35, then 35 to 40, and so on and so forth. And so the heights of these bars correspond to the false negative rates. So in other words, they correspond to the proportion of people in that age group that would have paid back the loan, but were denied for the loan. And so what do you notice? Yeah. Right. What this is showing us is that over 60% of people in the 20 to 25 age group were denied a loan even though they were going to pay it back. Right. So of all the people in the 20 to 25 group who would have paid back their loan, 60% of them weren't even given the loan in the first place. Right? And so we can see the false negative rate decreases as the age group increases. So who do you think is sort of being treated unfairly here? The young people or the old people? Yeah. Yeah, the young people, right? Because the false negative rate is bad. Right? You're being incorrectly rejected for these loans. You want that to be low for everyone, or at least maybe the same for everyone. Right? And so here's what we're going to do. Instead of looking at 7 age categories, let's just make a single age category. Is young. And this will match what we said before. Right? Someone will be young if they're under 25, or old if they're above 25. If you talk to anyone above 25, they'd be pretty mad at this because I don't think they think they're old. But anyways, it's not us, so it's fine. So here's what we'll do. First, we will look at whether or not our loan classifier achieves demographic parity. Remember, demographic parity is achieved if your classifier predicts 1 just as often for both groups, right? Or if the proportion of times it predicts 1 is independent of the group. And does it seem like our classifier achieves demographic parity here? No, right? So what this is saying is it approved 68% of the old people's loans and only 29% of the young people's loans, right? If there was demographic parity, these numbers should be similar or the same. It doesn't seem like there is, right? And actually, it's so different that there's no point in running a permutation test. There's no way this could happen by chance unless you had 4 people in your data set. Right? We have hundreds of thousands. This is not going to happen by chance. Do we agree? Okay. Note that this number is not factoring in whether or not they were correctly or incorrectly rejected or approved. Right? This is just saying it approved 68% of the old people's loans and 29% of the young people's loans. Right? Those approvals may or may not have been correct, but this is just talking about the approval rate. Do we agree? Okay. So that's demographic parity, or the lack thereof. Now let's take a look at accuracy. So now what I'm doing is I'm looking at the accuracy of our classifier for old people and the accuracy of our classifier for young people. And what do we notice here? They're much closer. right? And so maybe it's the case that our classifier achieves accuracy parity, right? Because if it did achieve accuracy parity, its accuracy should be the same for old people and young people. Do we agree? And so these numbers seem similar, but they're still not quite the same. And so there's a question, right? Are these two numbers the same in the population and this difference is due to random chance? Or are they actually different? Is this difference significant? Is this significance, is the difference significant? Okay. So I already mentioned this, but what's the right tool to determine if this difference is significant? Yeah, permutation test, right? When does a permutation test apply? Well, it's when you have some numerical attribute across two groups. And here the two groups are young and old, and the numerical attribute is the accuracy of our classifier. And so what we're going to do is just say, okay, under the null, the accuracy is the same for old people and young people, and the difference is due to chance. And to simulate data, we will just randomly assign people to be either in the old group or the young group, figure out their accuracies, and find the difference between them. Yeah? So in the bar chart before, there we were looking at the false negative rate. This is the accuracy. They're not the same metric. Because the false negative rate doesn't look at the false positives at all, and it doesn't look at the true negatives at all, right? So there's other like factors that play into the accuracy, right? Yeah, that's a good point. Okay, so the question is this difference significant or is it just due to chance? And so like I said, here's what we're going to do. Randomly assign people to either be old or young. So then we'll have an old data set and a young data set. We'll find the accuracy of the classifier in the old people, the accuracy of the classifier in the young people, and then we will compare those accuracies. Our test statistic actually will be the difference in accuracies. Right? So our observed test statistic could be this minus this, because that's the observed difference in accuracies for our classifier. Do we see why this would be our observed test statistic? It's like actually how different were the accuracies. Okay, so the code is all here. You can refer to it later on if you want. But notice we are not retraining our classifier at any point. We're just using the predictions it already made. Okay, that's important. So in your step 4 of your project 5, you should not be retraining anything. You're just using the classifier you already made. And that's all this is doing. It's randomly shuffling people to either be in the old group or the young group. Once it's sort of assigned people to groups, it's finding the accuracy of the classifier in each group, and it's taking the difference, young minus old. Okay, and what do we notice? Yeah, so the null was that the accuracy was the same in the two groups, and differences were due to chance. In other words, the null was that there is accuracy parity, right? And so if there were accuracy parity, the difference in accuracy we should expect to see in the two groups is no more than like 2% either way. The difference in accuracy we actually saw in the two groups was like 5%, which is way too large to have happened due to chance if there were accuracy parity. And so here it seems like our results are not consistent with the null, and so we would reject the null that there's accuracy parity. It seems like there's not accuracy parity. Do we agree? Okay. And so, before we talk about that, what I'll point out is that we could have done this same permutation test for any other metric, right? It could have been accuracy, it could have been precision, it could have been recall, could have been any of these evaluation metrics we wanted to use. Right? Essentially, all you were doing is thinking of two groups, which here we engineered, right? Like there wasn't a young and old group before, we just thresholded. But we made two groups, and then we compared the performance of our classifier in the two groups. Do we agree? Okay. So there's a question of ethics, like, is it fair to deny younger people loans more often? Right? There are two ways of thinking about this question. Well, if you're the bank, you might say, yeah, that's fair, because younger people default more often. And remember, default means don't pay back their loan. Right? And perhaps it is true that younger people are more likely to not pay back their loan. Right? And so if you're the bank, you're going to say, well, since I know they're young and they're not going to pay back their loan, I'm just going to reject them more often. So my overall accuracy is high. Right? And so from the bank's perspective, denying younger people more often might seem okay. Right? But what about our perspective as young people? Well, we would say, well, that's not fair, really, right? Because then how am I ever supposed to borrow money as a younger person, right? I need it to buy a house or buy a car or whatever, right? And so from our perspective, we're like, well, you run a bank, your job is to give us money. Like, sure, there's risk involved for you, there's also risk involved for us, right? And so there are two sides of this coin here, but it turns out the federal regulations prohibit lenders from looking at age when deciding whether or not to give someone a loan. Right? They do look at a bunch of other things, like your income, the age of your credit profile, your credit card balance, stuff like that, but they aren't allowed to look at how old you are. Right? And ideally, they don't look at anything that is strongly correlated with how old you are either, but sometimes that can be tricky. Right? So if they were allowed to look at employment length, for instance, someone who's been employed for 30 years is obviously at least like 40, probably closer to 50. Right? Whereas, we haven't been employed for that long, so, our employment length is going to be strongly correlated with our age. So ideally, they're not using age, and they're also not using things that you can use to predict age, right? Of course, it's not perfect, right? Because length of your credit profile, like how long you've had a credit card, essentially, that is used in determining whether or not you can get a loan, and that is correlated with age, right? So it's tricky, but there are federal regulations around it.